My fault. I usually do, but for whatever reason, didn't do it. But I will post videos of class. All right. So let's take a look right here at this point. Looks like 0.4 comma 30. And so what does that point represent? What does that point represent? Let's see. I saw you first.
The rate of change in the sex population at 0.4 months.
Okay, so which is what? He said the rate of change at 0.4 months, the rate of change is 30 insects per month. Agree with that? Okay, so is the population at 0.4 months, A, let's take a quiz, A, increasing, B, decreasing, C, staying constant, or D, you can't tell. Everyone have their answer? How many people say A? How many people say B? Oh, I'm so happy. Okay, good. All right, yeah. So the rate of change, when Y is it increasing? It's going down, right? Isn't it going down? Okay, yeah. So the rate is decreasing. This is the rate. The rate is decreasing, but the actual population itself is increasing because you have a positive rate of change. Okay, very good. I'm glad I didn't make that a real quiz. Okay, because that would have been a waste of time. All right, so let's go to the end here and just I'll work through the last exercise here. So I kind of tried to hold your hand and get you started on numbers 3 and 4, looking at a 0.2 month interval and figuring out what your population growth would be if you had these constant rates, and then asking which of those constant rates kind of would apply in this case. So with a constant rate at 20, 45, or 60, be something that's trying to pretend to be the actual rate in the first 0.2 months. Which one? 45, right? So 45 kind of is like something of, maybe we think of what, like an average of all those rates or something. Okay, and so then if you want to continue on, in order to find, so here's 1 month. We want to estimate the population at 1 month. So then, following that lead of 0.2 month increments, we could go through each 0.2 month increment and say, let's just eyeball what a constant rate would be, over that interval. So at 0.4 it was 30. At 0.2 it's something like, close to 60. So what about for the next 0.2? Yeah, so maybe a little bit less. So it's like 30 and then a little bit less than 60. So I'll just say 40. I think this one's supposed to go to the next one over. Okay. So I'll call this K1. That's my first constant rate, trying to be this actual rate, and that's 45. And then there's this second constant rate, attempting to be this changing rate, this decreasing rate, as one rate, and I called it 40. And then from 0.4 to 0.6, our rate goes from 30 to about 15. So I'll say 20. So that's our K3. So we're trying to recreate this changing rate function with constant rates by estimates, right? By estimates. From 0.6 to 0.8, let's say 15. So my K4, 15. And then from 0.8 to 1, it goes back up to 30 from 15, so maybe 20 again, or 20. Let's do 25 this time, or 22. Okay, but now I did not specify the 0.2 month increments. That was just if you were to run with what you did in the previous two questions, you would stick with the 0.2 month increments. But I didn't really specify that. So if you use a different size increment, it's okay. All right, it's okay. But this seems reasonable. There's only 5 constant rates. That's a reasonable calculation. And so what did we start? The population started at? So we want the population at 1 month. We need the initial population, 105. And then what are we going to do? We're going to use our mathematics of constant rate of change. So if for 0.2 months it had a rate of change of 45 bugs per month, how did it increase? How much did it increase? K delta x, right? 45 per month times how many months? 0.02 months, or 0.2 months. All right, and then we're going to add on how much it increased according to this next constant rate for 0.2 months. And so on. $15 and $22. And so we have the initial population plus the estimated increase for each 0.2 months, which we do by K delta X. Okay, and then you should have gotten something like 135 or 140. Is that right? So about 135 to 140 insects. And if you reported a final answer with a decimal, 135.6, that's not good, right? Because what are we talking about? Insects. So we're estimating the total population of insects. So that estimate's got to be a whole number, right? Estimate's got to be a whole number. Okay? Okay, so that was the idea of the assignment. And notice what's not on my graph. What is not in my graph? Rectangles, right? Rectangles. Because what we used to think of as area is now we're trying to reproduce the rate graph with constant rates. So functions don't have vertical lines and they don't have rectangles. Okay, so this is just like a chunky function, right? It's just pieces of different constant functions trying to mimic that rate function so that we can calculate a change in this population. Okay. Any questions on the homework? So that's an overview of the homework. Okay. So another way, so this was based on, we were estimating, we were trying to do, just by eyeballing, we were trying to find the best rate possible for each interval. Okay, so there's another systematic approach that doesn't try to estimate by eyeballing, but it just keeps a system, and that is instead of trying to guess the best constant rate, you just take the actual rate at the left side of the interval, and you let that be the constant rate for the whole interval. Okay, so this is an alternate way, and this is called using the left approach. Uh-huh. Yeah, it's just we're thinking about it as adding up amounts of change rather than adding up areas of rectangles. Yeah, so it's the same exact idea as a Riemann sum. So using the left approach, so now in the first 0.2 months, we say the constant rate isn't our eyeball estimate, but we're just going to use the actual rate at the left side of that interval, or at x equals 0. What would it be? 30. So 30 is the actual rate at the left side, so we're going to have a constant rate of 30 for that whole interval. Boom. And at 0.2, from 0.2 to 0.4, what's the actual rate at the left side of the interval? 57, something like that. It's whatever this point is. So we're going to use that rate to be the constant rate for the whole interval. And then at 0.4, back at 30, right there. And then at 0.6, from 0.6 to 0.8, what's the actual rate at the left side? 14, 15, something like right there. Okay, and then from 0.8 to 0.1, we're going to use the actual rate at the left side of that interval. The actual rate is like 18 around, so right there, or 20. Okay, and then we do the same thing. Okay, so we do the same thing. So this is a valid kind of way you could do it systematically without trying to eyeball the best rate in each interval. Okay, so now this becomes your K1, K2, K3, and then you do the same thing as before. Okay, and since we're summing, so every time we do K delta X, right? They're all K delta X. All of them are K delta X. So instead of writing out a bunch of them, in this case 5, but in another problem it would be 10. So we have a shorthand way of writing what? We have a short way of writing the sum of the same thing over and over again. You should have seen this before. It's Greek sigma. Okay? And we say we're gonna let the subscript, we want 5 different rates, so we're gonna say K sub I or J or whatever you want, and then I equals. First I is 1, and then the last I is 5. So this is just not meant to be scary symbols, but meant to be convenience, right? It's saying take K1 times delta X, then plus K2 times delta X, just like I wrote out in the last, when I did the actual problem. Okay, so this is called summation notation. It's a shorthand way. It's meant to save you, risk, save your risk from writing. Because if they all look the same, let's just write it once and explain how it's going to change from one to the next. And the only thing that's going to change is just the value of K. K1, K2, K3, K4, K5. And so when you see that, you think this. You see this, you think this. You see this, you think this. Okay? Okay, so let's go back to the flag, and let's look at the flag example again, so we can continue on our. Continue on our journey of what's our goal? Our goal is, well, let's do that. Let's just do a little review here. So what do we got so far? We've actually done the first, we're making sense of the fundamental theorem of calculus. Okay, we're making sense of this. And so what is that for? That's for calculating an amount or an amount of change of some quantity. And we said the principle number 1 was constant rate of change. If you're going 80 miles an hour, none of you do, right? But if you're going 80 miles an hour, and you go for half an hour, how many miles do you go? 40. Right, because what'd you do in your head? You did 80 times 1/2 hours. Okay, you just did K delta X. You just did K delta X to get change in Y. What was your K? K was your rate, 80 miles an hour, and you multiplied by the change in time, 1/2, and that gave you your change in distance, 40. So by saying 80 miles per hour times 1/2 hour to get 40 miles traveled, you just did delta Y equals K delta X. Okay? So that was the first principle. And then so we said principle number 2 was realistic rates are usually changing rates. And so that's our flag. And so how do we handle that? We said we're going to make a pretend rate function. Right? We're going to make a pretend rate function and we're going to use constant rates that are trying to mimic that one so that we can use principle 1, right? So we can use principle 1, we'll just have to do it lots of times, right? We'll have to do it lots of times. So we're going to mimic the rate function with constant rates so that we can apply principle 1. And we're going to add up the changes to estimate the total amount of change, right? That's what you did in your homework, and that's what I just showed you. So we've made it through the first 3 principles of the fundamental theorem. And then I just showed you the total change is going to be the sum of a bunch of k delta x's. Any questions so far? So let's take a look at the next principle here. So here is that changing rate function for lowering the flag. The red is the actual realistic rate function. And now I'm showing a pretend rate function with constant rates where delta x is 0.3. Delta x is 0.3, and I'm using a left approach. Okay, so the blue step function is delta x is 0.3. Oh, by the way, so someone asked me after class, when are we going to get to the problems of this course? Okay, so I'll just let you know, a big portion of the first exam is this stuff, okay? Because I write the exam, okay? So I'm not wasting your time. I'm not wasting your time at all. Okay, so delta x is 0.3, and we're using the left approach in order to generate this pretend rate function. So let's just take a look at it without. I guess I have to turn off this. Let's try that. There we go. Okay, so how, with delta x equals 0.3 and a left approach, let's just make it faint. How about? Can you still see it? Perfect. All right, so it's nice and faint. So with delta x equals 0.3 and a left approach, how are we doing at estimating or reproducing the actual rate function with these constant rates? How's it doing? Good or bad? Or kind of good or kind of bad?
It's a little high.
So if you were to see it, if you didn't know what the rate function was, and I just showed you that pretend rate function, would you know what the rate function was? No, you wouldn't really know what's going on there. Okay, so what do we want to do? We want a better pretend rate function. We want a rate function that's better, that pretends to be or mimics our actual rate function better. How can I do it? Okay, yeah. So more intervals make delta x more frequent. So here is delta x equals 0.2115. Would you be able to guess now what it was? It's not great. Not great. Here's 0.1348. Okay, so it's kind of, you see that most of the time it's the negative 0.75, so we know that's important. All right, let's make it smaller. So every time I make delta x smaller, okay, so every time I make delta x smaller, it's a smaller interval, so those constant rates are doing a better job staying close to the actual rate function. So, yeah, let's make it really small. Okay, that's still a bunch of constant rates. But in the back of the room, what does it look like? It looks like the original rate function, right? So it's doing a really good job. So for a really small delta x, it does a really good job reproducing the original rate function. Okay, so now let's use those constant rates and calculate the total change from 0 to 3. Ready? Want to do it? What's that? No, so I want to find the total change now using these constant rates. Yeah, it's going to take forever, right? We'll be here till midnight, okay? So, because there's so many. So it's like the trade-off, right? If you want something better, you got to work harder for it, right? If you want a better approximation, then you got to spend more time. If you want something quick and easy, it's not going to be a very good approximation. Okay, kind of how life is often. Okay, so, but this is the next principle, that if you want a better rate function, you do more smaller intervals, and you're going to get a better pretend rate function out of constant rates. Okay, until it's so small that you can't distinguish. Is this it? No. This one down here? This one. So it's virtually the same, right? Okay, so that's idea number 4, that if you make smaller intervals, you get a better approximation. And then if we could just make them small enough so that making it any smaller won't help us, it won't make a difference, then we can consider that kind of like exact, right? So we can get to a point where delta x is so small that making it any smaller won't make a difference for the rate function, then we've kind of arrived at the actual rate function in essence, right? In essence. Okay. Okay, so now I'm going to show you something else here over on the right graph. What's that? Yeah, we'll go back through it. Yeah. That's 4 and 5. So 4 is more intervals, more smaller intervals is a better approximation, and 5 is super small intervals can get us to essentially reproducing the rate function exactly. Essentially, okay. So now I'm showing another graph over here. I guess that's there. Pretty good. Okay, so I'm showing another graph over here. Okay, so notice that that's not the x-axis, right? This is starting here somewhere between 3 and 3.5. Okay? So I want you to interpret what are you looking at here relative to the situation. So with your partner, take a minute and analyze this graph completely. So everything you can say about this graph, be specific. What is that showing? Go. That's for you to figure out. He said, is it a rate of change graph? And I say, you tell me, is it a rate of change graph? Months, not months, seconds. Okay, did you figure it out? Some of you? So, who wants to volunteer and explain what's going on here? Yes, sir.
So like the flag being lower than the stopping because like as you're switching hands, it takes time to like switch your next hand and then going down, stopping, and then going down.
Okay, so okay, that's true. But my question is, can you interpret this graph for me? Tell me about the details of this graph. So yeah, but yeah, that's true.
I think the y-axis represents the position of the flag, and the x-axis
So what position?
the position in meters.
And we call that? What do we call that? Height. Right, yeah. You had the right thought. You just needed the word. Yeah. So this y-axis. Now I'm actually showing you the height graph, the actual quantity. So far we've lived totally in the land of rate of change graphs, right? So now finally I'm showing you the quantity graph, or just the height graph. Okay. And so the units on that y-axis will be meters. And what about over here on the x-axis? It's the same scale on the x. It's the same x, seconds. Okay. So so I got 4 points here. So this point on this graph over here is 0.7, negative 0.75. And this is 1.8. And negative 0.74, because I want it to be different. All right, and then 0.7 and 4.5, close enough. And then this is 1.8 and 3.8. Does that look about right? So 1 minute, interpret the meaning of those 4 points, each point. So interpret the meaning of each of those points. What do each of those 4 points mean? Go. Okay, so rapid fire here. Rapid fire. First point. That point right there means what? Right there. Yeah, in the green shirt.
Which point, sorry?
The first one right here. This one right here.
That's just the rate of change in the position, like how quickly it's decreasing.
So use the numbers to explain the point.
So at 0.7 seconds, the height of the flag is decreasing at a rate of negative 0.75 meters.
Okay, right. So good. All right, next one. Red shirt right in front of him. So this point. What does that mean?
I'm not sure.
Not sure? Okay, we'll go right in front. What do you think? What does this point mean right here? Not sure. We should be. This is just graphing, right? Right there, this point right here. What does it mean? Oh, this isn't calculus, guys. This isn't calculus. Blue shirt, Superman.
Yeah, it's at time 1.8 seconds.
Uh-huh.
The height of the flag is decreasing at a rate of 0.74 meters.
Good. This says that this point is saying that at 1.8 seconds, the flag is decreasing at a rate of 0.474 meters per second. Okay? Should be able to interpret points on a rate graph. Okay, let's come up to this one right here. So right here in front. What does this point mean right here? She said at 0.7 seconds, the flag is at 4.5 meters. Good. And then this one right here. Yeah.
At 1.8 seconds, the flag is 3.8 meters above the
Right. At 1.8 seconds, the flag is 3.8 meters above the ground. Good. So what I want you to do is, in 2 different ways, in two different ways represent the change of height of the flag from 0.7 seconds to 1.8 seconds. So I need to name these functions here. So let's name this function so we'll name that function R of t. Okay, and then we'll name this one H of t. So in two different ways, I want you to represent the change of height of the flag from 0.7 to 1.8 seconds. Go, see if you can do it. Talk. Okay, so I kind of jumped the gun a little bit here. So let's take a step back and talk about how do we get that total change using the pretend rate function, all the constant rates. It's the sum of a bunch of k delta x's, right? So what we wanted to talk about, which I should have talked about before we did this, was so then when that delta x gets small enough, when it gets essentially small enough so that the constant rate and the actual rate, there's really a negligible difference, how do we represent that total change then when delta x is small enough so that there's no noticeable difference between the amount of change that we calculate? So what do we have then to represent this when delta x is super small and we're getting an accurate total change? Yeah, and so what is that? Okay. That's what the integral is. The integral means that we're doing the sum of a bunch of a little changes based on constant rates, but the delta x is so small that there's no difference between what the actual change is and our estimate because delta x is so super small. And what is that called when delta x is so super small? No, delta x. dx. Okay, so this means sum, right? This means sum. And integral means sum. They're both foreign letters that mean S. Greek S and German S. They both mean sum. When delta x gets super small, we call it dx. And when delta x is super small, what happens to all these constant rates? They essentially be the continuous rate function, which is RT. So I should use dt. Is that what you're going to say over there? Okay, thank you. Sorry. So, sorry. we're using t. So this integral expression, integral is a sum, what? Of a bunch of little bits of change, k delta x. So that's k delta x in the sky. It's just that the delta x's are super, super, super small. And we're gonna like add a billion of them together. Okay? So these are two analogous notations. It's just one is for like big chunky changes, and this is for super small changes, so that the total change that we get is indistinguishable from the actual amount of change.
Shouldn't that be a definite integral though, because you set intervals an integral in the question?
Yeah, I just haven't gotten to that yet. Yeah, so what do you want to be from what to what?
From 0.7 seconds to 1.8 seconds.
Yeah, so from 0.7. So he wants me to put the starting and ending time for our example, and that's right. Well, for the summation, you don't actually put the x value or the t value where you start. Okay, you just count up all the rates, just 1, 2, 3, 4, 5, 6, 7. Okay, but it's here that we actually specify the starting and ending x, or in this case t quantity.
Wouldn't you set I is equal to 0.7?
No, I is 1, 2, 3, 4, 5. It's which interval you're in. It's counting the intervals. Okay, so this was one of the ways, right? So this is one of the ways then to represent the change in height of the flag from 0.7 to 1.8. The integral from 0.7 to 1.8 of r of t dt. But what I want you to recognize is this is the same thing as this. It's just this is for big chunky changes, and this is for a trillion little changes, such that we're getting the true amount of change, or an amount that's indistinguishable from the true amount of change, because we got those intervals to be small enough. Okay, so what was the other way? So there's our one way. Our one way to get the amount of change from 0.7 to 1.8 is this. What's the other way? Yes, ma'am.
H of 0.7 minus H of 1.
She wants H of, what's that?
0.7
0.7.
minus H of 1.
How'd she do? Is it right? Shaking your head? How do you calculate the change in a quantity? So you want to change it? Yeah. So we need final first. We need final first. Okay, so what h of 1.8 is our 4.5, right? So this right here, no, right here, sorry. This is right here, this is h of 1.8. It's the output of the function when the input's 1.8, right? And this is h of 0.7. It's the output of the function when the input is 4.5. And so how much does the height descend? This much. Right? It's the change in y. It's the change in the y coordinate. If the y coordinate is height, then it's just the change in height, which is the change in the value of the function from 0.7 to 1.8. So it's just final minus initial. So someone said, I don't understand why that makes sense. Does it make sense now? You got it now? Yep. Okay, yeah. Okay, right. So here, look. This is calculating, using the rate function, is calculating the actual amount of change. And then this, using the height, just using the actual quantity function, is calculating the actual amount of change.
Professor,
Yes, please.
so our height is basically our delta x, is what you're trying to say.
No. Delta x is little chunks of time. That's not horizontal axis.
Yeah, I understand that.
Delta y. It's a change in the y coordinates is our change in height, right? Because this was at 0.7 seconds, the height of the flag is 4.5. and this was at 1.8 seconds, the height of the flag was 3.8, which is h of 1.8, and that's h of 0.7. So to get how much the height of the flag changed, we're going to take the final height minus the initial height.
Perfect. Sounds
Better?
Thank you.
Yeah. Okay, we good? So these are both calculating the same thing. Therefore what?
It's the same thing.
Therefore, they're the same thing? What's the same thing in math? Equal. Equal. Two ways of representing the same thing. Look, fundamental theorem is starting to take form here, or it just did. Okay? Two ways of representing the same thing, using the rate and adding up a bunch of little changes from 0.7 to 1.8, or just taking the final value of height minus the initial value of height. That'll get that change in height as well. Okay? So the last thing is, how are the functions h and r related? How are the functions h and r related? Yes, sir.
H is the antiderivative of R.
Okay, therefore,
R is the derivative of H.
r is the derivative of h. Why? Because r is the height rate of change, right? This is the height, and this is the rate of change of the height. So this one is the derivative of this one, or like you said at first, the height is the antiderivative of its rate function. Okay, and so that covers it. So that we just hit all the principles. So we'll review it again in a second. But any questions about what I drew on the screen? Is it making sense? For some of you, maybe for the first time. Okay, cool. But that's what you should have learned in Calc 1. If you didn't learn it, that's what you should have learned at the end. All right, so let's. Can I erase what's up there? Let's go back to the summary. Constant rate of change, k delta x. Where do you see it? So now that we talked about that, where is k delta x in the fundamental theorem? Where is it? F of x dx. F of x is the rate. It's just a little teeny bit of the rate, right? And then dx is a little teeny delta x. Okay, changing rate is more realistic, so we got to do a pretend rate function. And if we want the total change using the pretend rate function, we're going to sum up a bunch of k delta x's. So, principle 4, make more smaller intervals, better pretend rate function, better estimate of total amount, better ingredients, better pizza. Thank you. I don't endorse any products, okay? So, principle 5, super small intervals. Super small intervals means essentially exact, and so then our sum of k delta x, we use this notation to mean the same thing when the intervals are super small. Sum of f of x dx. So in that expression, f of x dx, what is f of x? What does f of x represent? A rate, someone said it. A rate function. So whenever you have an integral, you're finding an integral, that function is a rate of change function. Did you know that? That's a rate of change function. Principle 6. Two ways to represent an amount of change. You can use the rate of change function and the integral, or use the quantity function itself and just do final minus initial, right? So this represents an amount of change using the rate function. This represents that same amount of change using the quantity function, final minus initial. And then the last principle is that quantity function, capital F, is the antiderivative of the rate function, little f. Why? Because f is the derivative of big F. Because it's its rate of change. Okay, so solving these problems. So we don't want to do this. Why? Because it would take forever, right? It would take forever to try to do something like that by hand. Or it would take a really long time if we got our intervals small enough. So what do we want? So what makes it convenient? Instead of calculating an amount of change by thinking about the rate and a bunch of little amounts of change that we're adding up, instead we want to find the antiderivative, or just the quantity function, and then it's easy. Then we just plug in the final value to get the final value of the quantity and plug in the initial value of x to get the initial value, and we do this instead because that's a lot more convenient. But that means finding the antiderivative. That means we need to find the big F is the antiderivative of little f. So we got to be, if we want to do it the convenient way, if we want to find this amount of change using the right side, that means we have to be good at antiderivatives, which is a big chunk of this course. And if we want to be good at antiderivatives, we have to be good at derivatives, okay? Because it's not a whole new set of rules. It's all the same rules, but now we're going the other way. We're going backwards instead of, so all those rules that we had to take the derivative, we're going to think about those rules in reverse. So let's practice that. Okay, first some notation. So whenever you see this notation right here in red, that in red means the same thing as what's in the box there. It means plug B in, plug A in, and subtract just like that. So those are equivalent. That is equivalent to what's inside the box. So you'll often see it, like in textbooks, you'll see it both ways. Got it? Okay, give you 20 more seconds. So we didn't really talk about this one. We just talked about this one. This is actually the whole thing we just talked about in terms of making a function out of it, making an accumulation function, and that amount of change being variable. But we just talked about the second way. Okay. All right, going on. Let's see, we can do this we'll do this for homework. There we go, that's what I want. So, in that first expression, what does x to the fourth represent? A rate of change. So now when you look at an integral like that, you say, oh, x to the fourth is the rate of change function. It's the rate of change function. Okay? And so if we want to solve this integral, it's going to be the total amount of change. So we're going to practice interpreting first. So what is the meaning of this? Who wants to take a stab at it? What does it mean? What does that whole expression mean? Somebody knew. Somebody. Yes, sir.
Well, it's the sum of the rate of change function from whatever x values are 1 to 5.
Okay, are we summing up rate? So it sounds like you're saying you're summing up the rates. Is that what you're saying?
So you're finding the sum from 1 to 5.
Okay. So it's a sum from 1 to 5. Red shirt?
We're trying to find the total change.
Total change.
1 and 5.
1 and 5.
On an infinite number.
Okay, so this is a good start. It's the total change of 1 to 5, from 1 to 5. The total change of what? Total change of what? Yeah. Okay, and what kind of thing is the antiderivative? So like, what does that mean?
The rate of change.
Okay. So yeah, so like the y value. So in a situation, what's the general? So there's some quantity, right? So there's some quantity. So total change of some quantity. You're thinking the y value, And what do we know about that quantity?
And it's changing at a rate of x to the fourth over an infinite number of infinitesimally small intervals along 1 to 5.
Okay, yep, of some quantity whose rate of change is x to the fourth. So that's what that thing means. It means a total change of some quantity as x goes from 1 to 5, and we know the rate of change of that quantity. The rate of change of that quantity is x to the fourth. So now we want to calculate that amount of total change. So that whole thing is just a value. It's a number. It's some amount of change of a quantity. And so we want to calculate what that is. What do we need to do that? The antiderivative. So we're thinking backwards, and we're thinking what function, if you took the derivative of it, would be x to the fourth. So okay, so it's so last you said x to the fifth. You're going to raise the power. But if we took the derivative of x to the fifth, what do we get? We get 5x to the fourth. We don't want 5x to the fourth. We just want x to the fourth. Therefore, over 5, or you just throw a 1/5 on there, and now. Okay, so the way that I teach antiderivatives is kind of something of a guess and check method. And so where does the check come in? How do you check? Take the derivative. You're going to take the derivative. So don't be afraid to make a stab at it, right? Because all you have to do is take the derivative, and if it's not right, then you know you're going to adjust it. Okay? So don't be afraid like you got to get it right on the first try. Just go for it. So just make an educated guess, and then check it by taking the derivative. All right, so that is our quantity function, because here's its rate function. So that's our quantity function, and what do we want to do? We want to do from
1 to 5.
and that's the notation that means the final value of the quantity is 1/5, what? 5 to the fifth, right? That's the final value of the quantity, and the initial value of the quantity is 1/5, 1 to the fifth. Final minus initial. Yeah, so it's the same. You just use the same quantity function, plugging in 5, plugging in 1. Okay. So I think we get 25 minus 1/5, or 24 and 4/5. 24.8.
Wouldn't be 125 be 1/5 of 5 cubed?
Which is 5 squared.
But it's 5 to the fifth, not 5 cubed.
Oh,
So
yeah.
it would end up being
5 to the fourth.
6,324.
625.
Give that man a prize. 5 to the fourth. And so 624.8? Thank you. Please. Tell me. So that was good. You just got it right away. Is it right now? So 624.8 means what? Means what? Total change when x changes from 1 to 5?
Whatever y was increased by 624.
Right. Right. Whatever y, whatever that quantity was, whose rate is x to the fourth, it increased 624.8 units. Okay, so I want you to, with the person next to you, so for these you're going to interpret the meaning of the expression. Practice that. And then find its value. Right? Okay, so I know it's monotonous and it's warm in here, but it's really good practice to keep interpreting, keep practicing the meanings of these, okay? Because what good is it if you don't know what it means, right? What good is it if you don't know precisely what it means? So, get a partner. First, take turns. Take turns talking through the meaning. And then find the value.
E to the 1/3.
No, it's still 3 in the end. Because the 3 will not because it's constant, so it becomes 3 times the integral over the interval of the x. It's still 3 to the x.
All right, let's do some derivatives here. Derivatives. That's okay. This will help remember it. Derivatives. So all these have a constant multiplied by them. So what's this derivative? And where does the 32 come from? 4 times 8 to the 7. Okay, derivative.
10 to the 10 cosine.
And cosine.
Yeah.
Derivative. When constants are multiplied by a function and you take the derivative, what happens to the constant? You just hold on to it. It just stays. So when you do the antiderivative, what happens to the constant? It just stays. Just stays. If we're doing antiderivative, 4, 4, 10, 10, 20, 20. So when constants are multiplied by functions, whether you take a derivative or antiderivative, it just comes along for the ride. Just stays like it is. Where it is and like it is. Okay?
Oh, there's a thing.
Oh, did the air just turn on now? Now I feel air conditioning. Yeah. I'll talk about the last one. Oh, so I just moved.
Oh, you have to like take out the screw and put it to the 1.
Okay, let's regroup. Let's regroup. Here we go. So how about Colorado shirts? Back there. Yeah. Can you tell me the meaning of this integral right here? Where am I? There we are. This one. What's the meaning of that right there?
Ln is the sin x is the function of the rate of change.
It's the rate of change, okay.
And so the whole thing is the antiderivative got from -1/2 to 3/4.
Okay, so antiderivative is what we do to solve it, but it's not really the meaning of what this is. So try again or pass? That's all you got. Okay. How about next to her, right there? White shirt, glass. No, in front. Yeah. What's the meaning of this expression right here?
From the interval of negative 1/2 to 3/4, the derivative changes sign x.
Okay. Still not getting the meaning. Okay, volunteer.
And you're finding the total change from those 2 points, or in between those 2 points for the y-axis.
Okay, so total change between those 2 points. We got bits and pieces here.
Total change from
Let's see. He's
Total change from x equals negative 1/2, x equals 3/4 of some quantity whose rate of change is 7x.
well said. Did you hear that? So it's the total change of some quantity as x changes from negative 1/2 to 3/4, where that quantity's rate of change is sine x. The total change of the quantity. Okay? Antiderivative. So to do it, we want the antiderivative, which is? What function would give a derivative of positive sign? We're saying what function's derivative would be positive sign? That's negative cosine. And then you're going to plug in 3/4 and plug in negative 1/2 and subtract. Whatever that is. That's exact value. So leave it as an exact result. That's fine. Okay, so let me just give you a preview here of what we're going to do next, and that's this last one. Okay, questions? Any questions about the first three? Questions about the first three? Okay, so I'm going to give you a preview. So this last one, if we're thinking of that as a rate of change, we're thinking of that as a derivative. What rule is that? What rule was used to get that derivative? No. What derivative rule? The chain rule. Okay. Do you see in the chain rule? How do you see that it's the chain rule? Because you would do the derivative kind of in the big picture. So that's what we call g prime of f. So we started with a function g of f of x. And what do? You do the derivative in the kind of in the big picture, g prime, leaving f as it is. And then by the chain rule, you chain on f prime of x. So here's the pattern. The interior, its derivative is the other factor in the equation. Do you see that? And that's what we're looking at here. The interior is our x squared plus 3, and there's its derivative, 2x. So it matches the result of the chain rule. So some of you, most of you have learned U substitution. Okay? And if you want to stick with U substitution, you are more than welcome to do that. But some of you I would like to take on a journey to a new frontier, to something better. Okay? And so basically, if you can work at this and get it, you can do ones like this in about 1/3 or 1/4 of the time that U substitution takes. But it takes really knowing derivatives really well. Okay? Recognizing that this is the chain rule. And what did we do to get here? So this is our g prime. So what did we do to get here? We reduce the power of this, right? So if we're going to go backwards and do the antiderivative, we're going to do x squared plus 3 to the what? 3/2. So essentially, this antiderivative is just this. But we just have to clean up the mess. We just have to clean up the mess. So how can we check this? How can we check this to see if it's equal to that? Take the derivative, right? Take the derivative. So this is what we're going to call our first attempt. First attempt is we just go for it, based on an educated guess, based on undoing. We're going to call it undoing the chain rule. Okay, undoing the chain rule. And so then we're going to take the derivative of the first attempt. And the derivative is 3/2 x squared plus 2 to the 1/2 times 2x. How did I do? Is that right? 3. Okay. And then we compare. So if these are identical, then we got it on our first attempt. But if they're not, then we just have to clean up the mess. So is it identical to that? No. And we're off by what factor? 3/2. So how would we adjust our first attempt so that when we take the derivative, the 3/2 won't be there? 2/3. We're done. See? Put the 2/3 in front here. Plus C, or not plus C, because we're going to do it in indefinite. And then we're going to evaluate from 10 to 35. So if you get good at that, and you can do it much faster than use substitution, if you can get good at that. So we'll practice that. But if you want to stay with use substitution, I can't stop you. Check Blackboard for the complete details of the homework. Okay.